Welcome all. In this lecture, we will discuss about what exactly is rolling and pure rolling. Then, what is the influence of moment of inertia in rolling? And after that, we'll be discussing different shapes. Like, for example, there is a solid sphere, there is a hollow sphere, and there is a cylindrical rod, and then there is hollow cylindrical member. So when these roll without slipping, I mean pure rolling, which one will reach the ground faster if they are released from a particular inclined plane? And why this is happening? Why they are not reaching at the same time? All these it will be discussed, and the significance of moment of inertia will also be explained in this session. So, and one more thing. So I have something like this. So if I rotate about the central axis, why it is moving faster? So if I rotate about some other axis which is away from the center, what is happening? All this I am going to discuss, and I will try to demonstrate in a practical manner so that there will not be any problem, my dear students. So that, chalo. Before that, let's see what exactly is pure rolling. Let us take now. Let this be the ground. Okay, no problem at all. Now on this ground, let us take a shape something like this. Okay, no problem at all. It may be a disc. It may be a thin, maybe a ring, maybe a disc, maybe a sphere, maybe hollow sphere, solid sphere, whatever it may be. Now, rotation plus translation is rolling. No problem at all. And I am not going to give all the details about pure rolling, exactly what is pure rolling. All these I had explained very clearly in our mechanics class plus. But here I am going to give you just an idea about pure rolling. And then under pure rolling, when different objects, how the moment of inertia is influencing, we will see in a detailed manner. Chalo. Now, let the velocity of this center of mass, my dear students, let the velocity of the center of mass be VCM. Okay, no problem. Means what does it mean? Means all the points on this member, they translate at VCM. Okay, let it rotate. Let the angular velocity be omega. Please note down that this angular velocity is always for a body. I repeat, it is for a body, not for a point or so. Because, for a rigid body, for example, if this point makes, for example, if you take one point, if it rotates by an angle theta, other point will also make an angle theta, because it is a rigid body, there is no relative motion. So therefore, d theta by dt will be same for the complete body. No problem at all. Now, let the radius of this member be r. And you know that the tangential velocity is, as it is rotating, so it will be r omega. And here, as it is rotating in clockwise direction, here the tangential velocity will be r omega. And here the tangential velocity is r omega. Absolutely fine. And here it will be again r omega. Look at. Let us superimpose this. As VCM is the velocity of the center of mass, all points will translate with this velocity. So if you see at the contact point, this has a velocity VCM. And for pure rolling, there should not be any slip. So if VCM is more than r omega, it will slip in forward direction. And if VCM is less than r omega, if r omega is more, it will slip in backward manner. So whenever it is slipping, please note down that it is the kinetic friction that comes into picture. Whenever it is sliding, so as there is a relative motion between both, kinetic friction will come into picture. Now, if VCM is equal to r omega, if VCM, this linear velocity is equal to r omega, so at this point, there is no, for example, let this be stationary. I repeat, let this contact surface, let it be stationary. So when this is stationary, what will be the velocity of this point which is at the contact? So this is r omega, this is VCM. If both are equal, I am not saying they are always same. If they are equal, now at this point, the net velocity is 0. It means when the net velocity at the point of contact is 0, means there is no relative velocity between, already the ground is stationary, Now this point is momentarily stationary because v is equal to r omega. So here the velocity is 0. It means both this ground surface and the contact point at that instant they have no relative velocity, and that is known as pure rolling. For pure rolling, at the instantaneous point, at that instant, the velocity is 0. I mean, relative velocity is 0 between the contacting surface and the point of contact. I'm not saying the velocity is 0. If this surface moves with some velocity, this point will also move with the same velocity. What I mean to say is, under pure rolling, there is no relative motion between the point of contact and the ground surface. So as you assume the ground surface to be stationary, this point of contact will also have 0 velocity. That is pure rolling. And one more thing. Under pure rolling, the velocity of center of mass is equal to r omega. Exactly. We know that for pure rolling, this r omega and VCM should be same. There is no slipping. Are my dear students, when there is no slipping at the point of contact, means both are stationary. At that moment I'm talking. When both are stationary, what friction are you going to expect? It is the static friction. So in pure rolling, it is the static friction that plays a role. But in case of rolling with slipping, when it slides, there is a kinetic friction. Okay, now let us differentiate this. So dvcm by dt, radius is constant, and this is d omega by dt. And you know d omega by dt is alpha, r alpha, and this is acm. So therefore, under pure rolling, the acceleration of center of mass, that is a, is equal to r alpha. Please note down that if it is slipping, if it slips, v is not equal to r omega, then a is not equal to r alpha. Only under pure rolling I can write the acceleration of center of mass as r alpha, where alpha is angular acceleration. Wonderful. Yahan tak there is no problem at all. Now you may be wondering, sir, this point has a 0 velocity. Very good. This point is momentarily stationary. But why, if it is stationary, why it is rolling, why it is moving in forward direction? Great. Don't think that when the velocity is 0, the object should always be stationary. Even when the velocity is 0, next moment it can have a velocity if there is an acceleration. Because when you are starting a bike, initially the velocity is 0, but after 2 seconds or 1 second, your vehicle will move somewhere because it has acceleration. Similarly, there is an acceleration which is in this direction omega square r. As there is acceleration, therefore at the next moment it will try to move, even though instantaneously the velocity is 0. So please note down that after some time this point may reach somewhere, new point will come in contact. So that new point at that time has 0 velocity under pure rolling, 0 relative velocity with respect to ground under pure rolling. So these are the basics. With these basics, let us move now. Now, observe, my dear students. With these basics, let us move. Wonderful. There is a member. Please note down that this may be solid sphere, this may be hollow sphere, this may be thin ring, or it may be ring, or it may be like hollow cylinder, or it may be solid cylinder. It may be any shape, and you know that. But before we go to that, I want to tell you one important point here. Observe here. Take one member. Let this be, I will take any radius r, any radius r. Let us say it is rotating about this axis, let it rotate. And you know, if it rotates with an angular velocity omega, it has at this point, as it rotates, it has the linear velocity, that is the tangential velocity at this point, which is, I'm talking about this. Let the mass of this be, I have taken a small element, let the mass of this be some m or dm, no matter what it may be. So I have taken a small element whose mass is m. I want the kinetic energy of that mass. It is rotating. So what is kinetic energy? Half m v square. Very good. So kinetic energy is equal to half m. What is v square? V is equal to, this is the velocity, v is equal to r omega. So r omega whole square. So therefore kinetic energy is equal to half m. This is r square omega square. Wonderful, sirs. Now observe here. You might have observed certain things. Under linear motion, velocity is v, and in rotation, the velocity is omega. Means v is corresponding to omega. Okay, half, and m is corresponding to mr square. My dear students, when the member is translating, the inertia is represented by mass m. If mass is more, starting is difficult. When it is at rest, it may difficult to start the motion, and if it is moving, it is difficult to stop the object with heavy mass. Yaar, if we have a big truck, let us say big lorry, so let us say you are pushing, as the mass is very large, so therefore initially it is at rest. If you push, you need it's not easy to start. Similarly, if it is moving, and stopping is also not that easy. That is known as, in translation, inertia is represented by m, and in rotation, just this is rotating. Just observe mr square, mr square, v square, omega square, half. So in case of rotation, the inertia is represented by not m, unlike pure translation, it is mr square. What do we mean by mr square? M is mass of the member, and r is the distance of this member from the axis of rotation. Jis axis se ghum raha hai, it is representing that. What does it mean? For a given mass, if say for example, this is the axis of rotation. So the mass is here, okay, and another mass is, let us say, here. Look at, this is R1, this is R2. Definitely observe here, the moment of inertia of this about this will be mr1 square. And what is the moment of inertia of this? It will be, for example, the mass is m2 r2 square. So it means its moment of inertia is more. Means moment of inertia is representing the distribution of mass from the axis of rotation. If the mass is distributed away from the axis of rotation, its moment of inertia will be more. So what physically it represents? If the mass is distributed away from the axis of rotation, it will be difficult to start the rotation. And if it is rotating, it is difficult to stop. Very good, sirs. Now I'll give you a simple example. Dear students, let us take this. Dekho. Now let us take this. Now, about this axis, it is rotating. Dekho. And you know, it is easily, kitna easy hai dekho. It is easily rotating. Now I want to rotate, because if you see, the mass is distributed. So this is the radius. The mass is distributed up to this only. Now what I do is, I will rotate it not at the center. So at the center, this is the radius is. Now this is the distribution of mass. If this is the axis of rotation, originally I rotated about this axis. The distance is r. This is very less. So mr square will be less. But now I want to rotate about this. Look at, oh my God, it's not easy. You just see. So as the distribution of mass is away from this, it is difficult to rotate. Dekho, ghumana is not that easy. It's not easy to rotate. So if you just see, oh my God, you just see how fast it is rotating. And what about this? As the mass is distributed away, from the axis of rotation, it is away. Again, from the axis of rotation, away. As more mass is distributed away from the axis of rotation, देखो कितना difficult हो रहा है. And that's why आप कभी देखें, when वो लकड़ी लेके like he fights, he'll hold at the center and he'll do like this, because the moment of inertia. If he holds at the end, more mass is there, he cannot rotate like this. That is the beauty, my dear students. So if someone asks you what is the significance of mass moment of inertia, you should tell it shows the distribution of mass from the axis of rotation. If more mass is distributed away, then it will be, you know, my dear students. So dekho, then it will have more moment of inertia. That's why flywheels. And you know, cycle ka wheel dekhe na, it is more mass is away. So therefore, starting may be easy, but once it starts, it has more inertia. Therefore, stopping is not that easy. Aram se ja sakte. Ek baar initially it may be difficult. That's why finally it will be very easy, because if the you know Newton's second law, Newton's law. What is that Newton's law? If a body is in a state of motion, it will continues to be in a state of motion, and if it is at rest, it will try to stay at rest. So therefore, if the moment of inertia is more, it may starting is difficult, stopping is also difficult. Very good, sirs. Now kuch beauty dekhenge, sirs. Now let us take an inclined plane which is inclined at an angle theta. Now before that, I want to tell you one more thing. In my regular classes, I have derived the mass moment of inertia of different shapes. For example, if it is a ring or hollow cylinder, and for this I have derived in my regular classes on class, it will be mr square. Very simple, sir. If it is the ring, all the mass is located at the same radii. Therefore, total mass r square. Next, then what is the moment of inertia of hollow sphere? Hollow sphere, and this is 2/3 mr square. What is the moment of inertia of what I say? कौन सा ले लेंगे sir? A disc or cylinder, and that is your mr square by 2. And what is the moment of inertia of what I say, solid sphere? Solid sphere, it is 2/5 mr square. एक बार देखना सर, in all these mr square, mr square, mr square, mr square is common. So what is not common? This coefficient. So I will write this as 1 into mr square. I will write this as 2/3 mr square. I will write this as 1/2 mr square. I will write this as 2/5 mr square. So what I do is, these coefficients, I will designate it with some beta. So I will write this as beta mr square depending on the shape. So geometry. Therefore, beta will be 1 if it is the hollow cylinder. Beta is 2/3 if it is hollow sphere. Beta is 1 by 2, that is 0.5 for disc. Beta is 2/5 if it is a solid cylinder. So very good, sirs. So conveniently, I'll represent the moment of inertia as something like this. Let me check once. Ring mr square, hollow sphere 2/3, solid sphere 2/5, and disc mr square by 2. Okay. I will write. We will take 4 shapes, sirs. Disc, solid sphere, hollow sphere, ring. Chalo. I can represent by beta mr square. अब देखेंगे, sirs. Now let us start our experiment. There is an inclined plane. Now it is rolling without slipping. Let us take this as pure rolling. Let us take it as pure rolling. Very good. If it is a pure rolling, and you know, abhi to derive kiya, V is equal to R omega. The acceleration of center of mass is R alpha. Already I have derived this, and there is no slip. When there is no slipping, what friction is going to act? It is the static friction. Ab dekho. With respect to this, it is rolling and sliding down. Pure rolling, rotation and translation. Pure rolling. Okay. So with respect to ground, it is trying to move in this direction. So friction opposes relative motion. So with respect to ground, relatively it tries to move like this. Relatively it tries to move downwards. So friction will act in the upward direction. I repeat, sir. With respect to ground, this object is sliding. Sorry, I'm wrong. I'm sorry to use the word sliding. It is rolling. It is rolling. Means with respect to this, it is moving in this. So therefore, now I write, my dear students. So as it is moving like this, friction will oppose the relative motion. So therefore, this is the frictional force. Hope the direction is clear. So I have resolved this mg into 2 components. One is this component which is normal to the plane. One is parallel to the plane. This parallel to the plane, as it is theta, opposite will be sin theta, and our adjacent will be cos theta. And there is a normal reaction. Wonderful, sirs. अब carefully देखेंगे सर. Now we'll try to analyze things in a beautiful manner. अब देखो. Now you know that torque is equal to I alpha. ये तो पता है आपको. And this is rotating like this about this axis. It is rotating. So I is about this axis. What will be I? Beta mr square. Beta can be anything depending on the shape. Okay. Now you tell me. This mg sin theta is passing through this. Normal reaction is passing through this. Mg cos theta is passing through this. Of course, I should not see that already mg is passing through this. So therefore, these two will pass through this. No problem. And which one is responsible for torque? Only friction. So if the radius of this is r, and the torque will be equal to Ff into this length. This is r. This is r. This is r. This is r, my dear student. So therefore, Ff into r. This is r will be torque. So Ff into r should be equal to I. I will write I as beta mr square depending on the shape into alpha, which is angular acceleration. Wonderful. Already you know alpha can be written as A by R. Alpha can be written as A by R. So it is pure rolling. That's why I'm writing this. So therefore, Ff into R is equal to beta mr square into alpha. What is alpha? A by R. Absolutely fine. So same thing I wrote. अरे यार टॉर्क केवल एक ही फोर्स रिस्पॉन्सिबल है टॉर्क के लिए, एफ एफ इंटू दिस रेडियस इज आर शुड बी इक्वल टू आई अल्फा एंड दिस इज द डायरेक्शन ऑफ एंगुलर एक्सेलरेशन बिकॉज द टॉर्क इज इन दिस डायरेक्शन. सो देयरफॉर r is gone, this r is gone. So frictional force is equal to beta ma. Very good sirs. Now let us apply Newton's second law. ध्यान से सुनो. Net force in which direction it is moving? Like this. So net force in the direction of motion is mass into acceleration. So mg sin theta is in this direction, ff is in this direction. So net force is equal to mg sin theta minus ff is equal to mass into acceleration. I repeat, net force in the direction of mg sin theta minus ff. So net force is equal to mass into acceleration. Now already you know, dear students, ff. What is ff? Beta ma, and that should be equal to ma. So therefore mg sin theta is equal to, let us take on this side, तो ma को कॉमन ले लेंगे. I will take this on that side. So ma is common. So 1 plus beta. So mm is gone. So therefore I will write the acceleration as, देखो I want acceleration g sin theta by, I want acceleration that is g sin theta by 1 plus beta. This is very, very important. So the acceleration is independent of mass. It depends on the angle and it depends on beta, which is the coefficient of moment of inertia. देखो अब ले लेंगे g sin theta by 1 plus beta. Okay, so the acceleration is given by g sin theta by 1 plus beta. Absolutely fine. एक बार चेक करो सर. Beta is for a ring and hollow cylinder. It is how much? 1, I think. Ring or hollow cylinder. उसके बाद beta for hollow sphere. This is hollow cylinder, and beta for hollow sphere is 2 by 3, which is 0.667. and beta for किसके लिए सर? For a disc or solid cylinder, it is half, that is 0.5. and beta for sphere, solid sphere, and beta for solid sphere is 2 by 5, which is 0.4. अब देखो सर, कॉमन सेंस, जिसका बीटा ज्यादा है, if beta is more, it is in the denominator, acceleration will be less. Which one has less acceleration? If beta is more for hollow cylinder. So therefore its acceleration will be less. So what is the meaning of this? अब देखना सर. Let me apply my equation. And is it a constant acceleration or variable acceleration? It's not varying with time. So it depends on what. Let's say I'm not changing theta. So let us say one particular object. Let us take one at a time. So if I take hollow cylinder, it will be 1. ये भी fix है. Theta fix है. G is fixed. So therefore my acceleration is constant. When my acceleration is constant, I can use my equations of motion. So I will write S is equal to ut plus half at square. And initially it is released if the object is released. देखो sir, if the object is released from rest, and please note if it is released from rest, initial velocity is 0. Now let it cover a distance of s. Let this distance be s. Dear students, let it cover a distance s. So what will be this distance? एक बार let it be h. Let the vertical height be h, and let it slide down. Let the displacement covered by this object be s. So is there any relationship between s and h? Yes. Sin theta is equal to, sin theta is h by s, or you know s sin theta is equal to h. I repeat sirs. So it is sliding by this distance. This is the displacement covered by the object. So s and the vertical is h. So sin theta is h by s. So therefore now I write, my dear students. So अब देखो initial velocity is 0, तो ये खत्म हो गया. So s is equal to half a t square, and this s is equal to 2s is equal to at square. No problem at all. No problem. Already acceleration is known. So 2s is equal to a. What is the acceleration? G sin theta by 1 plus beta into t square. So therefore t is equal to under root of, I want t. It is 2s into 1 plus beta by 2s into 1 plus beta by g sin theta. अब देखो सर, we are just changing the object. देखो एक बार, G is not changing, theta is not changing, displacement, all are covering same displacement. Let us release all at the same time. All will cover same displacement. All are placed on the same inclination. G is same. So therefore, अब देखते हैं sir. Now just observe. Displacement, all are covering same displacement. G is constant, theta is constant. They are released from the same plane. Now you tell me which one will reach faster. देखो, जिसका faster का मतलब less time. Faster means less time. So if you want time to be less, beta is in the numerator. So the one which has less beta, जिसका beta कम है, it will reach the ground faster. You see, now he may be asking in ascending or descending order of reaching time. So किसका beta कम है, sir? Solid sphere compared. So when beta is less, the time taken to reach will be less. So if I release 4 objects from the from the same position on an inclined plane, first one will be reaching. Which one will be reaching first? It is, देखो, first it will be solid sphere. It will take less time. First it will reach. उसके बाद it will be solid cylinder. उसके बाद hollow sphere, and finally उसके बाद hollow cylinder will reach. Wonderful, my dear students, wonderful. So this clearly shows that which object is reaching faster. Now I'll demonstrate. I'll show you that. If you see clearly who is going to win the race, let's try to demonstrate. Let me demonstrate and show you in a crystal clear manner. एक बार I'll try my level best. हाँ, एक second. I think we can see it. एक second. हाँ, दिख रहा है sir. Very good, very good. Now I am placing. This is the solid sphere. This is the solid sphere and this is the hollow sphere. ये hollow है, देखो अब रिलीज कर रहे हैं. तो देखो solid sphere beta is less, तो time taken will be less, so it will reach ground faster. Hollow sphere, what is beta? 0.67. 0.4 is less for solid sphere, so it will be less. And for hollow sphere it is more. You just see. अब देखो सर, रेस स्टार्ट कर रहे हैं, दोनों का रेस. एक सेकेंड. Yes. फर्स्ट सॉलिड रीच हुआ सर, फर्स्ट सॉलिड रीच हुआ, उसके बाद ये रीच हुआ. Sometimes he may be asking in examination, what are the velocities? So have you understood, sir? Wonderful, sir, wonderful, very simple, very simple. और यहां पे और एक बात है सर, वेरी गया देखो वो. अब देखो, will take solid cylinder. ये solid है सर, पूरा solid है, और ये hollow है. अब आप देखना, hollow will take more time. Hollow is 1, है ना? Hollow is 1, and then कहाँ गया? Solid कहाँ गया रे? Solid cylinder, it is 0.5. As beta is less for solid cylinder, it will reach faster. देखो एक बार. Oh my God, नीचे गिर जाएगा. Yes, wonderful, my dear friends, wonderful. So he may be asking you to calculate the velocities also. He may be asking you to calculate velocities. देखो, which one will reach? देखो, first it will reach. तो ऐसा क्यों हो रहा है सर? Because if the moment of inertia is more, which one has more moment of inertia? Hollow cylinder. Because all the mass is outside, so it is difficult to start. Because they are starting, difficult to start. That's why as inertia is more, it will take more time to reach. So this is and based on this, we'll be using many applications like flywheels, like bicycle tires. They are made hollow. All the mass is focused at the outside. And if you want the velocity also, अब ये भी करेंगे sir, क्या problem है? So let us try to find out the velocity also. इधर देखो. And you know, acceleration is equal to g sine theta by 1 plus beta, if I am not wrong. Let me check, sir. Let me say g sine theta by 1 plus beta. हाँ. Okay. You know that, सुनो, v square minus u square is equal to 2as. Why are you applying this equation? These are valid for uniform acceleration. Here the acceleration is uniform. So therefore, initial velocity is 0. So v square is equal to 2a. What is a? G sine theta by 1 plus beta into s. But already I have told you that either देखो, this is s, this is h, and this is theta. Can I write s is equal to, देखो, can I write, my dear students, क्या कहा है रे? Sin theta is equal to h by s. Yes. So v square is equal to 2, a is this into s. 2as. Acceleration is this, na? G sin theta by 1 plus beta. G sin theta by 1 plus beta. V square is 2as. Now you tell me, what is S sin theta? S sin theta. I'm sorry, इसको थोड़ा erase कर देंगे sir. It is G. ये तो 0 होगा. I will erase this. Don't worry. Don't worry. होगा ऐसा. आराम से. Tension मत लेना. Is equal to 2. A is G sin theta by 1 plus beta into S. 2as. What is S sin theta? S sin theta. S sin theta is H. So V square is equal to 2G. S sin theta is H by 1 plus beta. Or V is equal to root 2GH by 1 plus beta. क्या मतलब है सर? If you take a hollow cylinder, नहीं आ रहा है सर. Let us take hollow cylinder. This will be 1. So therefore, if this is 1, it will be root GH, because 1 plus 1 is 2, 2 by 2. And if it is a cylinder, if it is a disc or cylinder, for disc or cylinder, beta is half. अगर cylinder or disc is rolling down, beta is half. So V is equal to root of, क्या हो रहा रे, हाँ, है ना? Is it okay? Yes. इसको निकाल देंगे, क्या दिक्कत होगा? So therefore, now it will be beta 2GH by 1 plus beta. What is beta? Half. तो क्या होगा सर? ये beta is half for cylinder. This is 2 plus 1 is 3. This 2 will go to the top. So therefore, it will be 4GH by 3. Likewise, you can calculate, my dear students. So I will come up with many more questions on rolling with friction, because the problem will come rolling friction. So why are we not using the limiting friction? Because it is a static. See, static friction is self-adjustable. All these I'll come up with beautiful concepts. Thank you, my dear students. If you have loved it, please leave your comment. I'm not asking you to like or share. No, वो सब नहीं बोल रहा. If you really loved the concept, please at least you share your feelings or comments in the form of comments, so that it motivates us to do many more such series of lectures. Thank you. God bless you.